Hi, today I will explain about the mechanism of hydration of alkenes for 3,3-dimethyl-1-butene. These are the steps for the mechanism of hydration of alkenes. So now let's look at the first step, which is the formation of carbocation by protonation of alkenes. The carbon-carbon double bond in 3,3-dimethyl-1-butene contains a pi bond, which is the region of high electron density. The pi electrons are more loosely held than the sigma electron in sigma bond. Therefore, this region acts as a nucleophile or a site that can donate electrons. This H2SO4 serves as the acid catalyst in this reaction. As we know, within the H2SO4 molecule, the oxygen atoms are more electronegative than the hydrogen atoms. This leads to the partial negative charge on the oxygen atom and partial positive charge on the hydrogen atoms. This electronegativity difference makes the hydrogen atoms as electrophilic sites. So as we know, in a single bond there are 2 electrons. So the two pi electrons from this compound will attack one of the hydrogen atom of the H2SO4. We have to draw the curve arrow to show the attack, to show the nucleophile attack, if I am not mistaken. So as a result, the pi bond will be broken, like this product. The product will no longer have double bond or pi bond. And then this sigma bond, it also contains 2 electrons. So the 2 sigma electrons between these hydrogen atoms and oxygen atom will be pushed to the oxygen atom. Why? Because oxygen atom is more electronegative than hydrogen atom. So it will produce HSO4 minus ion. Now let's move on to the step 2, which is rearrangement. In the carbocation intermediate, a neighboring methyl group along with its bonding electrons migrate to the carbon atom carrying the positive charge. This results in forming a new carbocation at a more stable position. So in this step, the shift that we use called as 1,2-methyl shift. Why? Because the methyl group here, we arrange it with carbocation here. So it's like we change their position. The methyl will be here and the carbocation will be here. The results, the product is like this. And as we see here, secondary carbocation becomes tertiary carbocation, which is more stable than secondary carbocation. After 1,2-methyl shift, a more stable carbocation is formed here. This is the more carbocation. In this case, the positive charge is located on a tertiary carbon, which is more stable than the previous secondary carbocation. Now let's move on to the third step, which is formation of protonated alcohol adding H2O. So in this reaction, H2O ataupun water is the nucleophile. So the water molecule attacks the positively charged carbon ataupun tertiary carbocation that is formed in the previous step. By using what? By using its lone pair by using its lone pair. So dia akan forms a new carbon oxygen bond, ataupun we can call it as protonated alcohol. This the oxygen atom bears a positive charge due to forming the new carbon oxygen bond. So this is the last step, which is deprotonation of protonated alcohol. In this step, a proton or a hydrogen atom is abstracted from the positively charged oxygen, forming the final product 2,3-dimethyl-2-butanol. This ion or hydrogen sulfate ion is a base that attacks the proton on the positively charged oxygen atom. As usual, to show the attack, we must draw the curve arrow. So after the attack, the hydrogen oxygen bond will broken, and the electron from the sigma bond here will be pushed. The electron from this sigma bond are pushed toward the oxygen atom. Then the final product 2,3-dimethyl-2-butanol is formed after deprotonation. This is the product. It's important to note that using H2SO4 as a catalyst is important in facilitating the protonation of the alkene and promoting the subsequent nucleophilic attack by water. The acid catalyst is regenerated at the end of the reaction, making it a catalytic process. Means at first we use the H2SO4, and then dia akan kembali lagi jadi H2SO4 at the end of the reaction. So that's all from me.